What we're going to look at here is when two players don't have an incentive to move. In other words, when both players are playing strategies that make them choose actions in such a way that neither wants to independently change that. And so both are playing what are called best responses. And what we're really going to find out is an algorithmic kind of process with which we can always find these things. The game we're going to use as an example is this one. This is the coordination game. And the reason we're using it because there's actually three such pairs of strategies. So we're going to start off by looking at all the pairs of strategies where the players are told to play a single action all the time. So we know that sigma r will either be always take your first action or always take your second action. And likewise, sigma c will also be always take your first action or always take your second action. And so we're just going to look at these pairs and see if players have a reason to move or not. So if we take the first such pair, so sigma r, sigma c equals 1, 0, and 1, 0. So in other words, both players play the first action, then the utility to the row player of sigma r, sigma c is going to be 3. And the utility to the column player, sigma r, sigma c, is going to be 2. And now what we wonder is, does either player have a reason to move? So if we're here in this first row and first column, does the row player have a reason to move? So independently, and that's the important thing. So the column player is not moving, and does the row player have a reason to play a little bit of the second strategy more often? In other words, this 0, should they change that 0 every now and then? But every single time they do, they would get a score of 0, which is less than a score of 3, and so they would not get the best they could do, so they have no reason to move. 3 is in fact the best they could do against 2. And likewise, if we look at 2, and the column player considers moving to the other column, in other words, changing this 0 to something else, then the column player would, that tiny bit of time they do that, get 1 instead of 2, and so this 2 is indeed a best response as well. Now, if we take a look at a few other strategy pairs, because there's a few more that we need to go through. So when sigma r, sigma c is equal to 1, 0, and 0, 1. And so here we're saying that the column player is playing their second column, but the row player is playing the first row still. And in this particular case, what we have is the utility to the row player of sigma r, sigma c is 1, and the utility to the column player of sigma r, sigma c is also 1. And now what we have is this a best response are these best responses to each other? So if we're looking at from the row player's point of view, they're currently here. But if the column player, if they were to play their second strategy a little bit more often, in other words, change the 0 to anything else, then anything of the time, they would get 2, which would be an increase. So this sigma r is not a best response to that sigma c. And a similar calculus shows that the column player also has the same reason to move because they're currently getting that 1, but if they moved over, they'd get that 2. And so this is not a best response to that. So we have so far is one pair of strategies that is a best response and one that is not. And a similar calculus leads us to the conclusion that sigma r sigma c equals 0, 1, 1, 0 gives us that the row player's sigma r sigma t, the row player's utility is now 0, and the column player's utility is also 0. And in this particular case, sorry, I just realized that's not quite on the screen. And in this particular case, we again have that both players have a reason to move. We're here, and the row player could play the first row, and they would get a higher score. And likewise, independently, the column player could play the second row, second column, and get a utility of 3. So what we've got is not a pair of best responses. And the final one that we need to look at is sigma r sigma c equals 0, 1, and 0, 1. And in this particular case, what we get is that the utility to the row player of sigma r sigma c is equal to 2, and the utility to the column player is equal to 3. And here, if we look at this and we see that we're here, should the row player change their strategy, so the row player controls which row they're in, so if they were to change it every now and then, they would get a 1. And so that would be less than getting a 2 all the time, so the row player's got no reason to do that. And likewise, the column player is getting a 3. If they were to change what they're doing, they would get a 0 every now and then, so they've got no reason to change. And so what we have is that the first strategy pair is a pair of best responses, and the last strategy pair is a pair of best responses. These two in the middle are not pairs of best responses. Indeed, what they are is points at which a player can do better, right? Given what the other player is doing, one player can improve what they're doing. They're both not playing their best response. That won't always be the case. Sometimes one player is playing their best response and the other is not. But fundamentally, players have a reason to do something different. But at the start of this video, I said that there were 3 such pairs of best responses. So let's go find the other one. And the other one we're going to find, we're going to say, is it possible to find equilibrium behavior? In other words, behavior where players don't have a reason to move, where both players play both actions. Because at the moment, we've restricted ourselves to only considering strategies that indicate a single action, but are there strategies that are pairs of best responses that indicate to play both actions available to them? And so what we're going to do is we're going to say, all right, well, let sigma r equal x and 1 minus x. And importantly, we're going to say that x is strictly between 0 and 1. So x can't be 0, x can't be 1, because if x is 0, x is 1, that's just one of these cases we've already considered. And if we consider sigma c, and we'll just use a different letter, y and 1 minus y, and again, with y strictly between 0 and strictly between 1. And what we're going to do is use the general condition for a best response, which is something we've covered in another video, to essentially write down the equations that dictate what the value of x and y must be for these strategies to be best responses to each other. And so if sigma r is a best response to sigma c, then what we have is that, and this is the best response condition, A sigma c transpose I, so all the values of A times sigma c have to be equal to the maximum for k belonging to 1 and 2, the 2 possible actions of A sigma c transpose k. And this has to be true for all I in 1, 2. In other words, the utility to the role player of playing either of their actions must be equal to the utility, the maximum utility they can get. I realize I'm slightly off the screen. Put that bracket back, which is what we've got here. So we're going to go ahead and write down what this means. And because what we can do is we can write down an expression for this in terms of that, which has just got a y in there, and we can write that down. And what we've got is that if this is equal to the maximum, and it's also equal to the maximum for another value of I, then in fact, all we have is that they have to be the same thing. And so what that means in practice, we can writing this out explicitly, that 3y plus 1 times 1 minus y is equal to the max of A sigma C transpose K for K belonging to 1 and 2. And so that's the first value of I here. That's what I've written down here. And we've also got the second value of I, 0 times y plus 2 times 1 minus y. And if you're not sure where these numbers are coming from, they're just coming from the utility matrix A. And this has got to be equal to the same thing. Now, the important part here is not what value the same thing is, but that these two things are the same. Because now what we have is a linear equation in y, because we have, okay, thus 3y plus 1 times 1 minus y has got to be equal to 2 times 1 minus y. Indeed, just these two things have to be equal to each other. And so once we've done that, we can expand it out and we can solve the equation. We get y equals 1 over 4. And so for sigma r to be a best response to sigma c, for sigma r to be a best response to sigma t, for it to be possible to have a strategy sigma r that plays both actions, and for it to be a best response to sigma c, pardon me, y sigma c must have this value. And so essentially that's the point at which it doesn't matter what the role player does. This creates an indifference for the role player, and that's the only way that the role player will play all its strategies, is if it's indifference between all of them. And what we can do is write down the exact same, not the exact same equations, but very similar equations for the role player. And so we go that we need 2x plus 0 times 1 minus x to be equal to the maximum from k belong to 1 and 2 of sigma r b k, and 1x plus 3 times 1 minus x to be equal to the maximum of sigma r b k for k belong to 1 and 2. Again, the important bit not being whatever's on the right-hand side, but that these two things are equal to each other, because this is the condition for which sigma c will be at best response to sigma r. And so what we're doing is finding the point at which the utility of the first column is equal to the utility of the second column for a given value of x. And if we take a look at this, we have that 2x is got to be equal to x plus 3 times 1 minus x, which gives us x equals 3/4. And so we have 3 strategies altogether that are pairs of best responses. The two that we had earlier on, which were 1, 0, and 1, 0, both players playing the first role all the time. Then we also have 0, 1, and 0, 1, both players playing the second strategy all the time. And then we have 3/4, 1/4, and 1/4, 3/4. And so these three strategies, three pairs of strategies, are also pairs of best responses. What we've done here is a bit of an inspection exercise. We've kind of gone like, if they look like this, how can they find them? What value will they have? And what we're going to describe in the next video is an algorithm for doing this more systematically.